All right, guys, and that's time. How did you go? Did anybody finish? Yeah, got close, hopefully, maybe. Ish, so-so. Close. Some of the questions were, it could be a little bit of a time sink, I'm sure, if you got a little bit of time. So, I think the way that we'll go through this review, we'll go through number 1, because that's just a bunch of quick responses, and we'll just shoot those out of the way. And then, I guess, we'll do a quick show of hands to see which ones you thought were the hardest. We'll start there. We have to end this at 3:30. Like, we have to leave the room at 3:30. But if there's any hanging questions, I'm happy to stay with you guys. We can go find some other space, and maybe we'll just hang out up there and keep working on it. So, just kind of I'll do this qualitatively. Show of hands number 2. If people want to review that, it's pretty straightforward, easy. Number 3, yeah. That was a hard one. Number 4, yeah, quick, all right. Number 5, yeah, okay. So we're not doing hands anymore. Number 6 is okay. And then 7, yeah. 8, easy, straightforward, right? And then 9, yeah, okay. So we'll do 3, 4, 5, 7, 9, and we can change that order as we go. Okay, so number 1. We can kind of spitfire them. So A was what? Shout out. Macro, good. B, false, good. C, false, false, nice. D, true. E, 3. 5. Uh-oh. 4. Oh, we got a little bit of hesitation here. Okay, so we'll dig into that one. All right, so we've got 2.23 grams plus, and I think this is where some people might have gotten tripped up, 203 grams, right? It's 203 milligrams that we're adding onto it. And so when we're adding two numbers together, we keep the significant digits of the decimal places of the one that has the least amount of decimal places. So this one has the least, so when we add them together, we're dropping the 3, we're going to 12.43 grams. So that's 4 significant digits. Any questions on that one? Is that clear?
To keep sig figs at the lower.
For addition, it's sig figs past the decimal place. So if this was 2.2, we would only have kept 1. Because we don't know what's going on beyond this point. For this number, we do, but that could change depending on what this x is here. That could change what the other number is. So we have to drop that digit if we don't know it as well as we wish we could. Okay?
For multiplication?
For multiplication, you keep the least sig figs.
Period.
Period. Of whichever one is, and division as well. Least sig figs. Addition and subtraction. Okay, F. Spectroscopy, yep. G. Discussion. I would also accept error analysis, yep. H. Less. The wavelength, the peak wavelength absorbance of blue one is greater than that of, less than or greater than that of red 40. So red 40, because it's red, it means it's absorbing in the blue. So its peak absorbance wavelength is going to be something like 400. Whereas blue 1, the opposite is true. It's because we see the blue, it's absorbing the red light that's coming into it. So that means that its peak wavelength is at 700 nanometers. So 700 nanometers is greater than 400 nanometers. That's why it's greater. Any questions on that one? It's greater. Yeah. Yep. Oh, almost true. I. Erlenmeyer. Yep. Sometimes there's going to be simple stuff like that, just getting constant. Don't worry, guys. That's the easy stuff. J.
M1V1 equals M2V2.
Yep. M1V1 equals M2V2. M1C1 equals M2C2. What?
Is there an actual name for that equation?
There probably is, but it's just
writing that is fine.
Just writing that is fine. Yeah, that's what we've used all semester. K. Fume hood. Yes. I think a fume shroud might be a little bit contentious there because fume shrouds are really for like smaller gas-producing reactions. So you really want to do this in a fume hood if it's a gas-evolving reaction. Maybe it's if it's smaller, then maybe fume shroud would work. L. Hydrogen. Yep. N. Okay, so I am the boss of you. That's what that comes down to. Great, thanks. N. 0.05 to 1. Yep, great. O. Deionized. I'd also accept distilled there. P. Hot hands. Tongs. Also, that works fine too. Q. Oxidized. Yes. The reducing agent is reducing the other thing in the reaction. That's why it's the reducing agent. And then R. Why didn't we use mass spectroscopy? It's costly. That's one. That's a really good one. Just maintaining the instrument takes a lot of time as well. Another one that you could put is that it's more skilled, so it would be hard to train everybody on an instrument. But that's kind of more of a Gen Chem environment versus the so it's mainly cost. It's very expensive. Okay, so any questions? Any questions? Yes.
For C.
C. False. Oh, so about that one. So the empirical formula is not necessarily always more descriptive. It can be equally as descriptive as.
So that's what you meant. You're saying it can be equal to the molecular formula.
It can, yes.
Okay.
It can be equal to the molecular formula. It can never be more descriptive though.
Okay.
But that's okay. So the molecular formula, whatever, yeah. The molecular formula is going to be either more descriptive or just as descriptive. Yep. Okay, good for that. No any questions there? All right, so number 3. So, you want to do number 2?
Yeah.
Oh, okay. Rattle off the answers for all of them. Okay, how about that? We'll do that. We'll rattle off the answers and then we'll see which one of these stick around for if they were hard enough. Okay, so 2 is we have 2 iron nitrate, 3 sodium carbonate makes 6 sodium nitrate and iron carbonate. Is that right? Yeah? We'll go over it later. Okay, for 3, you can solve A, B, but you can't solve C. A is just a concentration calculation using the absorption spectrum. B is you just can use that concentration that you calculated and compare it to the grams that you dissolved. But you can't solve C because you don't know anything about EDTA or its molecular mass or anything like that. So you can't go forward with that. Yes?
Because the absorption is greater than 1, does Beer's law like still work?
So the tricky thing about that one is that the Beer's law was calculated at 550 nanometers. Right. So make sure you check what wavelength they were using in that. So even though it's not at the peak wavelength, which is what you prefer to use because you're going to get more deviance between different concentrations, it's way more accurate that way. This technician decided to do it at 550 instead. Who knows why? Maybe it was the range of the detector or something like that. But that was one of the tricks of the question. So you could work from there. If it was greater than 1, then you could say no, it won't be accurate, but we can get an approximation. Okay, 4, we've got A is a beaker. B, I would use a graduated cylinder. C would be a volumetric flask, because you want to know that 20 as precisely as you can. And then D would be an evaporating dish. Any other hanging ideas? Yeah.
Why couldn't you use a graduated cylinder for A?
For A, so you could. The thing about measuring acids with a graduated cylinder is that you're trying to kind of keep pouring more and more to try and get the volume right to 10. That kind of use with like a strong acid, it poses a bit of a safety risk. So if you're getting just approximately 10 milliliters, you just do a 1 swish into a beaker. That's safer than doing it multiple times, trying to hit the right volume using a graduated cylinder.
The keyword is approximately.
Yes, yes, approximately. You don't need exactly 10. You can get just a small amount and then measure it as your yes.
For C, could we use a volumetric pipette?
Volumetric pipette. If you have one large enough, then you can. And then you dissolve it in the stock solution, that should be fine. Yes, that can work too. Anything volumetric there. Yes.
For D, I put the funnel assembly. Is that only for some reactions?
Oh, so I was focusing mainly on glassware. I guess Buchner funnel is part glassware, but it also has like that top funnel part. That is also a fair point. Okay, 4 good? Yeah, okay. So 5, after we corrected the molecular formula, I got that you would need 155 milliliters of nitric acid and 26 grams of copper. Yes, maybe, no, maybe we'll go through that one. That's a solid maybe. Okay, I'm going to give that one a star. Then which reagent would you prefer to be limiting? Why? Suggestions? No? The acid to be limiting? I think that I would do the copper because it's more expensive and it's also heavier. So if you're trying to design a car, I don't know.
What about metal fragments shooting at you in the airbag?
You also have strong acid shooting at you in the airbag. This is a bad choice
true,
to
so.
begin with. So yeah, there's a lot of safety hazards. Which one's worse, the acid on your face or the shards? I don't know.
I'll take the acid, I think.
Yeah, we're already in a hard spot, and then you're about to get fired because it didn't work and it inflated all the way anyway. So this is a shit show.
Stan,
Yes.
should we just know that copper is more expensive than nitric acid? Or how do we determine?
Yeah, I guess I didn't give you any prices or anything like that. If it's not clear, so like nitric acid versus formic acid, and it's an important part of the question, we'll give you those costs. In general, metals take some more extraction. They tend to be more expensive versus something that's very commonplace like nitric acid. But yeah, you're right, that takes a little bit of intuition to get there. Like that you've just been working with it so much. So yeah, maybe that was a bit of a blind side there. Other question? Oh right, C. So the main one the main assumption that's failing here is that there's no other forces interacting on the molecules. It's the ideal gas law says that there's no other forces. It's just the static elastic collisions. But there's also going to be van der Waals forces, and that's probably going to bring the gas particles closer together, and that's going to be why your back doesn't inflate all the way. There are a couple other assumptions. I'm not sure if the volume element really plays into it, because you say that they're volumeless, but we're not getting the full volume anyway, so that's not the assumption that's failing us here. Okay, 6, for macroscopic representation, just draw like a white blob. That seems to work pretty well. And then what are some macroscopic properties you guys listed? White, smooth texture. Okay. What else? Shiny.
Shiny, tear resistant.
Tear resistant. Sure. Opaque. So what?
Thick.
Thick. Yeah. Density's kind of average.
Is it nylon translucent? Because of its linear polymer chain structure?
Maybe in the ideal world, maybe what was happening with our nylon was that I was getting a lot of air bubbles in it, so that's what was keeping the white look to it. But it should be translucent in ideal conditions. Okay, and then would it show up in a flame test? No, it doesn't have any metal cations. There would still be some sort of emission spectrum, but you wouldn't see it in the visible.
So does the color have anything to do with that? That's the fact that it's white?
No. Okay, for the thermite reaction, what I got was 3 ferrites and 8 aluminum goes to 4 aluminum oxide and 9 iron. Is that right? Yeah. That one was here. Okay, cool. Which reactant is the oxidizing agent? Aluminum. Is that right? So oxidizing means to make more positive over the course of the reaction. And the aluminum is the thing that got more positive. So that means that the oxidizing agent is the ferrite. Yeah?
So very
Ferrite is correct. And then if the reaction were to go in the reverse direction, which one would be the oxidizing agent? The aluminum oxide. Because it's a similar thing. It's the one that's more positive and it gets reduced over the course of the reaction, which means it's the oxidizing agent. Yes?
So The oxidizing agent is the one being reduced,
Yes,
which means that it's gaining electrons.
means that it's, yes, gaining electrons.
So then wouldn't the oxidizing agent be aluminum? Because aluminum is cation initial reaction, and
It's a metal, the metal aluminum is at a zero charge. Yeah. So when in a question where it says, if there's a metal involved and it says aluminum metal, you assume it's at the zero charge state. Okay, and then you would need 395 grams of aluminum. Yeah? Okay. All right, good. Then that one doesn't seem to be too big of a problem. Just big numbers. All right, and then number 8, what's the rule? You guys all know it. You go past the graduation that's listed, some sort of elaboration like that. And then what did you guys put as the reading? 29.12. So the tricky thing about burettes is that they read in reverse. You're going to experience that more in the next semester. So it would be actually 28.87.
Oh, hello.
Yeah. That wasn't really a test. I kind of forgot that burettes were upside down. You'll see that later. Don't expect a trick like that to trip you up on the exam. Okay, so the last one, it's asking you to think a little bit more critically about the setup of an emission scan and what we did. So what we did in the experiment was something very qualitative, right? We just burn it and see where the peaks are. But you can actually do it more quantitative, and the things that you would need to do is set the detector at a fixed distance and the nichrome wire so that you know that there's no fluctuation because you're moving the probe closer or further away. The other thing that you would need to do is you would need to have some sort of a standard curve that you develop as well with the concentrations. It's very similar to absorption spectroscopy, right? You're just trying to see how much signal do you get for this amount of copper, and also make sure that the volume that you're using is the same. So once you've got all of those parameters in check, and you make sure that there's you could make a comparison across fixed concentrations, then you can make the comparison with this unknown and figure it out. Now, making this all work, they have dedicated instruments for this. It would be pretty hard to do it in lab, and it would take several repeat trials, which is why we don't do it in lab. We don't have the equipment for it. But that's, if you wanted to do it more quantitatively, those are the things that you would need to do. Are there any other ideas that maybe I skipped over that you guys had for doing it?
Would doing it in a dark room make a difference?
It would be good for limiting the background noise, but if the background noise is affecting all of the standards the same way, then it's going to affect the unknown the same way, and you can still make that one-to-one comparison. Yes?
What are you measuring in the, like the standard curve? Like, it's not absorbent, so is it?
It'll just be intensity. It's going to be directly intensity. And yeah, we don't need to worry about Beer's law in this case, but we can still make the correlation between these atoms made this intensity, or sorry, this amount of atoms made this amount of intensity for these 5 samples, and ours falls in between, so it must be so
intensity versus concentration graph that you make the standard curve on.
Yes. Okay. That wasn't so bad, was it? Hopefully. These are, so the style of questions that you saw here are about the same as Janine's style. You might have seen on the practice exam that she posted as well. Did you all see the practice exam that she has up there as well? If there's questions on those, I didn't really review them as in depth, but we can also tackle those if we run or if we have extra time after going through what we have left over. So for 3, we'll go through A and B. So for A, we're asked to find the concentration, and we have a spectroscopy experiment that we can use. So that means we're going to be using Beer's law. A equals epsilon C. All right. So for epsilon, we have 5.1014 moles per centimeter. Path length, luckily, is 1 centimeter. That's going to be nice, but always make sure that when you're going through these kinds of problems, you check to make sure and you can assume that the Beer's law constant came from a 1 centimeter path length. Actually, no, you don't have to assume that. This already compensates for that. Whatever centimeter cube, it's already corrected for it. And then what we're looking for is C. So the absorbance, all right, we have absorbance, which equals 0.3 at 550 nanometers. Is that right?
I thought it looked more like 0.2.
0.2, that's fine, however, 0.2, 0.3, wherever you triangulate it. I put it at 0.3. So if you want to follow along with this answer key, use 0.3. But if you're getting different numbers, as long as they're within the same order of magnitude for whatever absorbance you got, then you're on the right path. So then what we have to do, we just take 0.3 divided by 5.105 or whatever, and then that gets you 0.059 volt. So that's A. Then for B, we're going to use this number. So in 100 milliliters, we have 0.0059 volts of the complex. That was just a quick, I guess the math that I did there was this times 0.1 liters, because we're in 100 milliliters based off of the question. So that's where we get this number. Oops, yeah, the error should go this way. So that's how many moles we have. We also know how many grams we dissolved based off of what the technician had written. So 2107 grams divided by 0.0059 equals 3711 grams per mole. That's the molecular mass of our complex. Any questions with those two steps? Yeah.
Going back to was any of the stuff diluted when you were writing the graph? Because it said spectrum of 1 milliliter stock dilution. So I wasn't
Oh,
sure
right.
if
Yeah,
that-
sorry. That's poor wording on my part. It's just the stock solution.
just
That's
stock.
good. Yeah, yeah. 1 milliliter. Right. If that was a 1 milliliter, and then I didn't tell you what was diluted
Yeah.
to. So yeah, then you would need that information. That's a really good point. So yeah, sorry about that. Just the stock solution was analyzed for the 1 milliliter. Other questions?
And then C we cannot calculate.
C we can't calculate. So what would you guys want if you could calculate it? Or if you want, what would you do next? Let's say I gave you the molecular formula of EDTA. What would you do next? What do you think? So we know the formula mass that we have here. And what's the formula mass of cobalt? 58.
58.93.
0.93. And then what we can do is we can subtract that number from this one. So we'll get something like 298 grams per mole. And that's whatever contribution the EDTA is adding to this. But our problem with finding the ratio is that we don't know if that's 1 molecule of EDTA, is that 10 molecules of EDTA? What is going on with this formula? We could just do a mass ratio of EDTA to cobalt, but we can't have the actual specific molecules ironed out. So for future reference, because you're going to be using a lot of EDTA next year, this is the formula of EDTA. The ratio is 1 to 1. So, bingo. But you don't have that kind of information based off the question. You would need to know what the molecular formula is of EDTA. And there's extra information that's given, this phosphate reaction. This was kind of harkening back to the practical when you had to do that, the gas evolving reaction and kind of backwards calculate. It's not helpful here in this situation because we already know how much cobalt we have to begin with. So we could figure out, I guess, the mass ratio in phosphate. Well, like we already know the moles of the phosphate. This would be helpful if we needed to know the moles of the cobalt that were in the original complex. But we don't need to know that because it's just 1 to 1. Or sorry, it's already given to us through the spectroscopy. All right, that one good? Okay. 4 we did, so that's done. And now 5. So 5a, it sounds like a classic PV equals nRT equation. So we'll just pop that up there. You can certainly expect to see a PV equals nRT question similar to this one. You can expect to see a spectroscopy question for sure, and then a lot of instrument stuff mixed in there as well. So let's make sure we've got it down pat. So the P here is going to be 1 atmosphere. The volume is 20 liters, as prescribed for the question. T is room temperature, which is 25 degrees Celsius, which is, we'll need to use Kelvin here, 298 Kelvin. And then R is given to us, 0.08206 liters atmosphere per mole Kelvin. PV divided by RT will give us our N, and doing that math, put it in the box, I got 8.18 volts of NO2 that we will need to fill that 20-liter bag. Yeah? No trip ups yet? So the next part of this, that's only halfway there. We can't stop just with that because the question asked us how much of the nitric acid and copper would we need to meet that goal. So from the reaction, we have a 2 NO2 to 4 HNO3, and then we have 2 NO2 to 1 copper atom. So that means for the HNO3, we're going to need twice of the amount of moles of HNO3, which equals 1.64. And then we'll need half as much copper, which equals 0.409. And you can get to that using the stoichiometry, the analysis, I forget the word for it. Dimensional analysis, yep. I just kind of did it a little bit more colloquially. So for every 4, we need 2, that means we need twice as many NO2. Or sorry, we need twice as many HNO3 to produce that much NO2. Okay, and then from there, now we know the amount of moles of HNO3 that we need and the copper that we need. So now we just need to convert that into the appropriate dimension, I guess. So this one is just going to be simple. We're multiplied by 63.55 grams per mole. And we get 26 grams of copper. Yeah? And then for this one, we'll have to do a little extra legwork. So 63.01 is the formula weight for nitric acid, which you can calculate from the periodic table. And then we'll need to use the density to get a volume out of this, because this is going to give us mass out, but we are using liquid. We're using the liquid precursor, so we need to get a liquid out, and we got the density there to use, 5.1 grams per milliliter. We're going to divide that number into the other. Yo, Jeff, how's it going? We're going to divide that number into the other because we want to cancel out grams and bring milliliters to the top. So that equals 155 milliliters HNO3. Did I get that wrong? Okay, so you multiplied these two and then divided that. It could be my math.
Are you sure you didn't multiply by 1.51?
It's possible I multiplied by 1.5.
Because that does give 156.
Yeah. 68.4?
Yeah.
Okay. So be it. My math was wrong. Somewhere in my calculator I messed up. Okay? Any questions with that one? Cool. And then which region we talked about that, and then we talked about the ideal gas law and the assumptions that failed us there, and why we should keep our jobs. Okay, and we were going to go to 5. Oh, we did 5 there. No, it's done. Okay, we're making good time. The only thing that we have to do now is 9. Which we did 9. Oh, okay, great. So done.
Wow.
Voila.
Thank you.
No problem, no problem. So, yes. 7A, sure. And I'm going to post this all online and scan it, and then I also have the video going. So 7A, I'll write it down. 3Fe3O4 plus 8AL goes to 4Al2O3 plus 9.
And it's expected that the Fe actually has like a fractional charge.
Yeah. Yeah. That's why I gave the equation for ferrite. It's not standard. I think 2 of them are 3 plus and 1 of them is 2 plus. So. Yeah. Yes.
Do you know where the exam's going to take place tomorrow?
I think Janine sent out an announcement. Did she? No? If not, then I'll message her. But everybody's going to be in a different place based off of the alphabet.
Yeah, we did that.
Or maybe you're taking me in 102. I'm not so sure.
You said something about people having to like sit on the floor.
Yeah.
Oh, then you probably take me in 102. The lecture hall. So, yeah, get there early. Get there early. It's going to be competitive.
Yeah.
And yeah, so I'll check in with you and make sure that you guys all have that clear. Okay? Cool. So if anybody wants to talk afterwards, we're really up here. Jeff, we're going to take over. Yeah, that's fine. And then we'll go meet out there with number 2. This is such a... You want to come back?
It's not connected at all to, this is not a section, so I've been like on my own.